So Klein-Gordon equation for a free particle. So for a particle of mass m and corresponding momenta, suppose we consider for a particle mass, corresponding momenta is px, py and pz moving under a conservative field of potential v. Suppose we are going to consider. In Cartesian coordinates, we can write the Hamiltonian exactly like this. H equals p squared by 2m plus v. Kinetic energy plus potential energy we know already. Corresponding operators in terms of components. Px is given as this equation, py is given as this equation, and pz is given as this equation we know already. Okay. Now the ordinary equation in the Hamiltonian form in the operator. We can write in terms of operator as exactly like this. Okay. E equals h psi equal to E psi. So instead of E you can write this. So you have this equation. So your total energy equals kinetic energy plus potential energy. And of course we have used the operator E equals I h cross t by dt. Now I am going to consider this potential as v equal to 0. So that means particle is free. I am going to consider. Okay. Then the velocity of the moving particle can be written in terms of the components x dot square plus y dot square plus z dot square. We know already. X dot square stands for dx by dt, dy by dt, dz by dt. So v can be written as exactly like this. Now we know that beta equals v by c. This is in specialty of relativity. Beta equals v by c. We are going to consider this term. And of course we know the relation with the mass of the particle which is moving nearer to the velocity of light, which is given as the rest mass divided by root of 1 minus v squared by c squared. We know already. So here v by c is termed as beta. So of course we know that the non-relativistic equation is the approximation of relativistic equation. When v by c tends to 0, the non-relativistic equation will become relativistic equation. No, relativistic equation will become non-relativistic equation. Okay, when v by c tends to 0, all the equations in relativistic equation will become non-relativistic equation. Okay, so E equals mc squared equals m naught c squared divided by root of 1 minus v squared by c squared. So we can substitute for beta equals v by c as m naught c squared divided by root of 1 minus beta squared. So we know that p equals mv. So m into dx by dt equals m naught divided by root of, correct, m can be written as m naught divided by root of 1 minus beta squared. Dx by dt can be written as x dot. So the component of the momentum can be written as px equal to this one in terms of x dot, py is in terms of y dot, pz in terms of z dot. Now you are going to add all the components. We will get total momentum. So we have px squared plus py squared plus pz squared equals m naught squared. Okay, m naught squared, and this will become x dot squared, y dot squared plus z squared divided by 1 minus beta squared. It is p squared. So 1 minus beta squared. Okay, this can be simplified as v squared. So m naught squared v squared divided by 1 minus beta squared. Okay, so now this beta squared divided by, we can write beta equal to v by c. Okay, we can write v squared as beta squared c squared. So beta squared c squared. This beta squared divided by 1 minus beta squared can be written as like this. 1 divided by 1 minus beta squared minus 1. Just take the LCM. Will give you 1 minus beta squared. Take the LCM. That will give you 1 minus 1 plus beta squared. 1 only to cancel. You have beta squared divided by 1 minus beta squared. So beta squared divided by 1 minus. So this term can be written as exactly like this. So instead of beta squared 1 minus beta squared, you can write 1 divided by 1 minus beta squared minus 1. Okay, is it okay? Is it clear? Beta squared divided by 1 minus beta squared can be written as this term. So we can replace this term as this term. So I have written the same equation. So I have brought this term to inside. So that will become m naught squared c power 4 divided by c squared 1 minus beta squared multiplied by this term. And c power 4 by c squared, that will give you 1 c squared. So minus m naught squared c squared. Okay. What about this term? This term is nothing but your e squared. See, this term is nothing but your e squared. Okay. This term, except c squared, that will become e squared. So e squared by c squared minus m naught squared c squared. Now we can write in terms of operators. So this equation can be written in terms of operators. So we know that p squared equals minus h bar squared del squared psi. So in terms of operator, you can write this equation as like this, which is equal to, your e will be I h cross d by dt. So you have to go with e squared. So that will give you minus h bar squared partial del squared d squared psi by dt squared. 1 by c squared is a 1 by c squared. Your m naught c squared, m naught squared c squared. Is it okay? Equation 8.25 to 8.26 in terms of operators. So we have written the same equation. Now divide by h bar squared minus h bar squared. So that will give you equation 8.27. So now we are going to divide this equation by minus h bar squared and just bring this term to left hand side. So right hand side to left hand side. We will have this term. As usual, this term can be written as del squared. So del squared minus 1 by c squared partial d squared by dt squared of psi will give you right hand side. This term can be written as square del squared. So de-elongation operator. So del squared psi, which is equal to m naught squared c squared divided by h bar squared psi. So of course we know that del squared is de-elongation operator, and this is consistent with space-time symmetry. So under Lorentz transformation we know already. So this is also known as Klein-Gordon equation for a free particle. Also it refers spin equal to 0. So you should not forget. So spin equal to 0. So this is equation is for k mesons and pi meson in which there will be no spin. Okay, not for fermions. So that's a discrepancy. This is not for fermions. That's why Dirac used another equation which we will see in the next class that includes for fermions. Okay. Now the plane wave solution of the form psi, which you have already seen, e power I kr minus omega t, is substituted in the equation 8.28. We obtain the energy eigenvalue exactly like this, e squared h bar squared omega squared, which can be written as exactly like this. Omega equal to ck, we know that. So omega squared equal to c squared k squared plus m naught squared c power 4. You just take the square root, that will give you e, which is equal to plus or minus this one. So this has positive energy as well negative energy. Mathematics is correct. So we have to interpret in terms of positron. For electron there will be a positron. For antiparticles proposed by Paul Dirac. This result is very significant in respect of two roots of energy. The energy of a particle can be either positive or negative. Okay, or negative. Thus a free particle relativistic quantum mechanics will have positive and negative energy values. So this will have both positive values as well negative values. Now in Schrodinger equation in quantum mechanics 1, after the derivation we studied about the probability densities, so which are very very important concept. We know that the particle or quantum particle should exist in some space. So we need to study about the probability density. The integration of the probability density should be equal to 1, normalization. So we know about this one. The same is applicable for relativistic quantum mechanics too. The same should be applicable. And of course we derived the equation. Can you remember that equation? That equation is known as equation of continuity. We derived this equation while studying probability density after the derivation of Schrodinger equation in quantum mechanics 1. We derive the same equation. That is the equation of continuity. Look at this equation. That equation also is invariant under Lorentz transformation. So look at this equation. ds by dx or ds by dr plus d rho by dt. What is S? Current density. What is P? Probability density. Current density and probability density. So both are of the same order. So it is space-time consistent, space-time symmetry exists. And we are going to check whether the same equation of continuity is applicable for relativistic equation or not. We are going to check. Is it okay? So we checked for non-relativistic equation, and similar equation should also be checked for relativistic equation. So we know about the Klein-Gordon equation is given by this equation, we know already. Okay, 8.3. We just multiply this equation by complex conjugate of the wave function. Okay, from left. So you have psi star del squared minus 1 by c squared d squared by dt squared psi, which is equal to, so this is, they are all constants, you can pull it out. So m naught squared c squared divided by h bar squared psi star psi. Now you just take the complex conjugate of equation 8.32. Just take the complex conjugate. So we are going to take the complex conjugate and multiply with the psi on right side. Take the equation, take the complex conjugate of this equation and multiply psi with the right side. Will give you psi star psi, which is equal to m naught squared c squared by h bar squared psi star psi. See, you are going to multiply this equation from left by psi star, first one, and second one, just take the complex conjugate, multiply with the sign on right side. Now subtract this equation minus this equation. Right hand side, look at the right hand side, both will cancel. So you are going to subtract only on the left hand side. So we are going to subtract on the left hand side. Is it okay? Right hand side will become 0. Is it okay? Now you pull this term, first term alone out. So psi star del squared psi minus del squared psi star psi. Is it okay? Okay, minus plus. So I have written front side in the bracket. Minus plus, and this minus somewhere here, which is equal to 0. Is it okay? I repeat. So you have psi star del squared psi minus this del square psi star psi, I have written like this, minus plus. So you have 1 by c squared, pull it out. So you have this term will become plus. So d squared psi star psi minus, you have psi star d squared psi by dt squared, which is equal to 0. So I have pulled del out. See, del out in this equation. So del psi star del psi minus del psi star psi, this term, and I have pulled one partial d by dt out. So that will give me this equation. I am going to divide on both sides by h bar 2im. Okay. So dividing this by h bar 2mi will give you this equation, and I have divided this by h bar divided by 2im. Already c squared is there, so I have written it. This term is considered as a current density. This term is considered as a probability density, which you have already seen in non-relativistic equation. This is your expression for current density. This is the expression for probability density. So we can write this as equation of continuity as del dot s plus dp partial dp by dt equal to 0, which is consistent with the space-time symmetry under Lorentz transformation. So this is the equation for the relativistic equation. So relativistic quantum mechanics. We have also obtained the same equation of continuity. Look at this equation, same continuity, equation of continuity. So this explains clearly about the probability density. Okay, suppose if del s equal to 0. For example, when r tends to infinity, we are going to check r tends to infinity, del dot is equal to 0. So that means partial dp by dt equals 0. That means p is constant. P should be constant. P is conserved quantity. If it is constant, probability is conserved. Okay, so it clearly explains that this is the equation of continuity, which exactly matches with the non-relativistic equation. Okay, so equation 8.39 is known as equation of continuity, and it is invariant with respect to Lorentz transformation, space-time symmetry. The current density S of r comma t, S depends on r and t, has the same form as a non-relativistic case. But what are P of R comma T? See, one C squared is there. Okay, but in non-relativistic case, this C squared will not be there. Okay, it is not consistent with a relativistic case. Any fluctuation of the current is compensated by the corresponding change in probability density. We know that when R tends to 0, the first term will become 0. The second term dp by dt equal to 0. It shows that conservation of total probability is ensured. Okay, conservation of probability. Now we are going to consider, as I said, this P of R comma T is not consistent. Okay, just now we said because of the existence of C squared. So now we are going to take P term alone and check the interpretation of physics. Consider the probability density. P is given as this. We know already. This is your P. Okay, so we are going to check. Now I can write this equation as h bar, that I am going to bring h bar I alone inside. So here remaining term will be 1 by 2 mc squared h bar divided by I. Multiply and divide by I. You have h bar divided by I. Multiply and divide by I. So that will give you minus I h bar. I repeat, you bring this h bar by I inside. So you have h bar divided by I. Multiply and divide by I will give you I h bar divided by I squared. So minus 1. So that will give you minus I h bar d psi star by dt. Is it okay? Plus similarly you have 1 I h bar will be there. So you can pull minus sign out. So that will give you plus. So plus psi star I h cross d psi by dt. What is this term? This term is referred as E. This term also referred as energy operator. So we can write this as E and this as E. Of course, E equals plus I h cross d by dt. What is this minus sign? You are taking the complex conjugate. Okay, and E must be a real value. Okay, E must be a real value. So E star equals E. Hermitian operator. H bar equal to H. So you have taken E out. Is it okay? You can take this E out. Will give you 2 psi star psi. 2 will get cancelled. P equals E divided by mc squared psi star psi. So this is the final expression for your probability. Okay, probability. But when E is positive, P will be positive. When E is negative, P will be negative. Wrong answer. If E is negative, the probability will never be negative. The probability will be always positive. Positive quantity. The probability, we know that probability is a positive quantity. But look at this equation when E is, because already we know that E has two values. One is positive value, another one is negative values. If E is positive, P will be positive, whereas E is negative, P should be negative. No other way. Now we are going to interpret in a different way, which shows on the slide. The probability density is positive when E is positive. When it is negative, E is also negative. The probability density takes both the values, positive and negative values. We know that probability density will be always positive, we know already. Okay, so due to this reason, Klein-Gordon equation was first discarded. So it was dropped earlier. But it was resolved by Pauli and Weishaupt in the year 1934. They said, if P of R comma T is multiplied by the charge, we are going to multiply on both sides by E. So that will give us EP. This can be interpreted as a electrical charge density. Similarly, J multiplied with E, that will give you electrical current density. Okay, hence it can be positive as well as negative value as long as it's real. So now you have positive value and negative value. Suppose if the system contains positive charges and negative charges, then this will work out. The system contains positive charge and negative charge. So the system will work out. So this is what they concluded. So the theory is useful only to a system of particles having both signs of charges. This can be regarded as a relativistic equation for a system of arbitrary number of particles and their antiparticles. So as I said, the system consists of positive and negative charges. It means that particles and antiparticles. Then this will work out. Okay. So this is what the reason behind reason behind this equation. If E is positive, P will be positive. If E is negative, P will be negative. However, you are going to multiply with small e, then we can say that there exists for a system which has antiparticles, both the things are positive, negative values and positive values are possible. Okay, so in this class we discussed the main thing, the first equation of relativistic wave equation as Klein-Gordon equation and corresponding probability density. Okay, probability density and current density we discussed. Okay, so we will see in the next class with Dirac equation, which is much more important, for which he became very famous and he got the Nobel Prize in the 1933. Okay, so thank you students, we will see in the next class. Bye.